Gravitational potential energy is energy that arises from the interaction between two objects that have mass. We can consider it to arise from the mass of one object interacting with the gravitational potential of the other object. This point of view is consistent with the units of gravitational potential, which you recall are joules per kilogram. This is the equation for the gravitational potential energy of a point particle. It depends on the mass of the point particle and the gravitational potential experienced by the point particle. This is not the gravitational potential of the point particle itself, but rather the gravitational potential of the other objects in the system that interact with the point particle. The gravitational potential energy of two point particles, A and B, can be considered to arise from the interaction of the mass of particle A with the gravitational potential of particle B. Alternatively, we could consider this gravitational potential energy to arise from the interaction of the mass of particle B with the gravitational potential of particle A. Either interpretation gives the same final expression, as we would expect from Newton's third law. It follows that the gravitational potential energy of a system of point particles is equal to the sum of the gravitational potential energies of each possible pair of point particles in the system. Now let's calculate the gravitational potential energy of this system, which consists of a uniformly dense rigid rod, denoted by A, and a point particle, denoted by B. We can consider this gravitational potential energy to arise from interactions of infinitesimally small bits of mass in the rigid rod and the gravitational potential of the point particle. Since these little bits of mass are infinitesimally small, we can model them as point particles and therefore use our equation for the gravitational potential energy of a point particle. In this equation, the infinitesimally small contribution to the total gravitational potential of the system depends upon the variable r, which is the distance between particle B and an infinitesimal bit of mass in the rod. The smallest value for the variable r in this equation is d, and the largest value of r is d plus L. These limits denote the closest and farthest any constituent point particle in the rigid rod can be to particle B. The total gravitational potential energy of this system is thus the integration of the contributions from each interaction between particle B and a point particle dm in the rod. In this equation, the mass of particle B and the gravitational constant can be taken outside the integral. We are then left with an integral that depends upon the variables dm and r. As we've discussed before for similar integrals, these two variables are coupled. Thus we proceed in our calculation by relating the infinitesimal bit of mass dm to a corresponding infinitesimally small length of the rod, which we'll denote by dr. The variables dm and dr are related by the linear mass density of the rod, which we'll denote by lambda. Upon substitution, we are left with an integral that depends upon dr and r, and is thus straightforward. Please note that since the rod was uniformly dense, the mass density lambda is a constant and can be taken outside the integral. We arrive at our final expression by substituting into our equation the expression for the mass density of the rod, which in this case is the mass of the rod divided by the length of the rod. Alternatively, we could have considered the gravitational potential energy of this system to arise from the interaction of the point particle, or the mass of the point particle, with the gravitational potential of the rigid rod, which we have already determined. As expected, the final expression for the gravitational potential energy of the system is the same for either interpretation.